Hi everyone, my name is Irfan Nafi, and today I'll be lecturing on Yolo, one of the most popular computer vision frameworks out there. So, Yolo stands for You Only Look Once, which is aptly named since its entire algorithm is only run once on the image, whereas other models will take multiple looks, so to speak, when processing an image. And because Yolo is generalizable and fast, it can be applied to a wide variety of applications, from autonomous driving to digital pathology through cell detection. In fact, the Taiwanese government has used Yolo in their Smart City Traffic Flow Solutions project to enhance city development. However, there are also key ethical solutions that arise when using computer vision models as powerful as Yolo, and I'll actually talk a little bit more about ethics later on. Finally, in this lecture, I'll put particular emphasis on talking about how older versions of Yolo work, like Yolo v3, but I'll also talk about some of the major things in Yolo v4 and v5. Alright. So, the development of Yolo started with Joseph Redman, aka PJ Reddy, and Ali Farhadi, in the unofficial version of Yolo v1. Around the same time, there were computer vision frameworks that were released, including faster RCNN, which used regional proposal networks, which were much slower but also more accurate. I'll talk more about RCNNs and how they compare to Yolo later on. Although Yolo is known for being consistently fast throughout all its versions, its accuracy was not very high in the earlier models. However, the later versions released in 2016 and 2018 made significant ground on accuracy, while maintaining the speed it's known for. In 2020, Yolo v4 and v5 were released, and although they're under different authors, both are still a significant jump from Yolo v3. Alright, so here are some of the different kinds of computer vision processes. You can have a model that can localize like just a single object, but there are also text-based computer vision models that associate keywords for an image, for example. You can also have models that can classify and detect multiple objects, which is exactly what Yolo does. There are models that can go even further and determine the exact boundaries for objects within an image through instance segmentation. And instance segmentation produces these things called masks, which, like I said, like they kind of like cover the entire area of the image. And yeah, mask RCNN is just one object. It's just one object detection and instance segmentation, a model that can do this. All right. So how do these kinds of systems work? More specifically, how does Yolo work? Well, here's a glance at the three main steps performed by the model when looking for objects. Yolo first splits up the image into S by S cells. In this case, S is 3. For each cell, Yolo predicts a certain number of bounding boxes that can be bigger than the cell itself. Finally, the model filters out low confidence and double classifications to produce the final bounding boxes. Now let's take a deeper look into each step. So, according to PJ Reddy, calculating bounding boxes directly gives an unstable gradient during training. This is solved by using something called anchors. But how are they determined? Well, anchors are just predetermined boxes that are generated when looking at training data. It turns out that there are statistical patterns between the ratios of boxes from the same class, as shown in the picture with cars. So, in the graph at the bottom, candidates for anchor boxes are being plotted, with the k-means algorithms trying to find the centroid for the cluster. In k-means, to find the cluster, you need to like have some sort of distance metric to know how far you should like adjust the centroid to actually be at the center. In this case, the distance metric is IOU, or intersection of over union, which is shown in the like the image at the left. Um, and if you put this like if you just like you put that graph in a log graph, you can see that there's like a clear statistical significance between the height and width. And this is exactly what anchor boxes are intended to have. So these anchor boxes are pre-generated per each cell and are decided with the process just described. So how are actual bounding boxes calculated then? Well, the network determines which anchor box is closest to a particular object size and shape, and then makes adjustments to produce the final bounding box, as shown by the image at the bottom. So usually what ends up happening is that you'll have an anchor box of like a similar size, and then the model usually like shifts it, or it can actually like change the size of the anchor box itself. But it's usually relatively similar in terms of the size and shape. Alright, so after predicting the bounding boxes from the anchors, we then have to filter out any results that aren't accurate or classify the object twice. The LV3 calculates a lot of boxes per cell, as shown by the image at the top, so this filtering method has to be good. The fastest way to get rid of most of these extraneous predictions is to set a basic confidence threshold. For any remaining boxes, you have to check double classifications. So if the boxes have like the same label with the high IOU, you should get rid of the box with the lower confidence. And this is shown by the image on the bottom. So let's look at a simple example. So here we have like a 3 by 3 cell, and there are two boxes per each cell. So S equals 3 and B equals 2. And in practice, Yolo actually like predicts around 63 boxes per cell, and S is 13. So there are actually 169 total cells, and this results in a lot of boxes. So for the cell we're looking at, the network outputs a vector y with the size b times 5 plus c, where b is the number of boxes per cell and c is the number of classes. In this case, the number of classes is 2 for a person and dog. 5 is there because of the p sub c, which is the confidence of the detection and the 4 attributes of the boxes, the coordinates for the top left, and the height and width. Since there are 2 boxes per cell, the vector's height is 2 times 5 plus c, which is 14. And by the way, the boxes on the image themselves represent anchor boxes. The model outputs attributes that are offsets of the anchor boxes as shown by the image on the bottom, which is then sent to the final output vector. The model does the same process for all 9 cells, which gets you a rather like large matrix or tensor with the dimension shown on the right. This diagram is also like probably more accurate for Yolo v2 because v3 takes a different approach where it makes predictions at various resolutions, resulting in an even larger tensor. Alright, so now that we have an idea of how Yolo processes its images, let's take a look at how it stacks up against other major computer vision frameworks like RCNN, which just stands for Regional Based Convolutional Network, or Neural Network, I guess. Alright, to process an image, one naive approach might be where you just like have a sliding window across an image and run your CNN models on every window to determine if any objects are there. This is a very inefficient process. So RCNN takes a more computationally effective method by selecting regions of interest where it thinks there might be objects. And these regions are called proposals. And each proposal is run through the network to get classifications. Now, it's pretty easy to see why this method is more computationally expensive than Yolo, since it runs its CNN model multiple times, since there are multiple regions. Yeah, and this is in contrast to Yolo only running its classification algorithm once. And yeah, that's just like how it extracts region proposals and then runs each proposal through its CNN network to classify. Alright, so that was an overview of some old versions of Yolo. Now let's talk about some more recent ones. So Yolo v4 is actually made by a different developer than PJ Ready, Alexei Bachkovsky. And this was due to some ethical concerns about how Yolo v3 was being used. For example, it was being applied on autonomous drone technology to target buildings, as one U.S. military general mentioned to him. And as that tweet shows, over time the concerns became way too great for him to continue. Now this is perfectly understandable, and I get why he stopped. But this also brings around an interesting ethical dilemma that I'll just briefly discuss. So there are several lines of ethical thinking, and one such line is utilitarianism, which is kind of how I look at computer vision research. Now, utilitarianism states that actions are right if they cause the greatest amount of happiness or benefit to the people affected. Computer vision is one area where utilitarianism is an interesting way of looking at things, because the effects of computer vision models like Yolo are not so black and white. So, for example, there are ethical concerns of computer vision beyond just military applications. There's a question of privacy. Facial recognition has come a long way, and governments can track where and what you're doing. In fact, China has already implemented a comprehensive citizen tracker that literally attaches a social score to citizens based on their actions. There are also concerns of discrimination due to non-representative training data. And oftentimes, when you the way you get the data might not necessarily be representative of the whole population. And this just means that it's not necessarily your model that's biased; it's the trained data itself. And yeah, so those are just some disadvantages or concerns about using computer vision, but there are also some clear benefits from computer vision. And one major one is that because it can be trained to be way more accurate than human vision, it can be used to diagnose medical conditions. So for example, it can look at chest X-rays or X-rays or MRIs to determine if pneumonia or even cancer is present. And oftentimes, they'll achieve accuracies well into the 90s, significantly higher than humans. Another implementation is with autonomous driving, as I'm sure you've seen with all the Tesla stuff going on. And on any given day, the most dangerous thing you'll be doing is actually getting into a car, where the chances of you dying are somehow magnitudes higher than from dying in a plane crash. And part of the reason it's so dangerous is due to human error, like from like having drunk drivers to like not having drivers being able to see something clearly. So it's obvious that like autonomous driving can save a lot of lives. So this was just a brief glance at some of the stuff surrounding computer vision ethics. But regardless, there are those that have continued the research, like PJ Reddy left off, and the work done by Alexi is recognized to be the official continuation of Yolo in the CV community at least, with PJ Reddy, even confirming so. Okay, so now that we have a bit of history about the model, let's get into the major improvements. So in previous models, the complexity of the architecture and overall algorithm was relatively understandable, as far as the understandability of computer vision goes. In V4, they upped the complexity with a bunch of minor modifications that together led to a significant performance and accuracy jumps. And one set of improvements is referred to as a bag of freebies, or BOF. And these are just a set of changes that don't affect the inference speed, but do affect the results. For example, V4 implements cut mix data augmentation, where a section of an image is pasted onto another image, which also means that the ground truths have to be adjusted. And another method is class label smoothing. So when training object classifications, not the object boxes, just the object classifications themselves, loss is usually calculated based on the confidence from the model compared to the actual object. For example, if the object is a dog, then the ground truth is 1. But the confidence from the model might be 0.2, 0.82. What class smoothing does is instead of setting the ground truth to 1, it sets it to something like 0.9 when calculating loss. And this is done so that the models don't classify an object with 100% certainty, because this might imply that the model is memorizing the object instead of learning, which is just another way of saying that this prevents overfitting. The other set of improvements added to YOLO v4 is called Bag of Specials, or BOS. And these are just a network. These are just a few techniques that impact the inference speed since they're directly involved with the network. Whereas BOF tends to modify the training data itself so that the model could learn better. And one example of a BOS method is with MISH activation. So this is an activation function inspired by swish activation. And swish is a gated version of sigmoid, where f of x equals x times sigmoid of x. Similarly, MISH is a gated version of soft plus, making the formula x times hyperbolic tangent of that entire mess, as shown in the graph. And MISH it has shown a significant increase in in baseline accuracy compared to swish and ReLU, with a 3 to 5% increase. And another thing the authors have implemented in the bag of specials is CSP, and this stands for cross-stage partial connections, which is a new CNN backbone. So this backbone reduces heavy inference computation by integrating feature maps from the beginning to the end of the network, resulting in reducing computation by over 20%. And this has even produced similar superior results in the ImageNet dataset. Now these are just just a few of the things included in the bag of freebies and bag of specials. There are way more stuff, both in the both that's involved in the backbone and that's just added for the data augmentation stuff. Yeah. So here's a graph that shows some concrete data on just how much better V4 is than other models. So on the y-axis, you have AP, which is also called MAP depending on your context, and this just stands for average precision. And It is essentially a way to determine the accuracy of a computer vision model by looking at the IOU of the model's bounding box predictions compared to the ground truths of the dataset. And what this just means is that like when you have when the model predicts a bounding box, it looks at what the bounding box should actually be, and the way it compares like how accurate the model's bounding box is that it looks at the intersection over union of the bounding box compared to the actual like box from the ground truth. And IU is a pretty good metric of doing that. And it's standard to measure the accuracy of this dataset from with the dataset from Microsoft called COCO. And this COCO stands for Common Objects in Context. And COCO is a collection of 80 just like general classes that have both mask and box annotations. And if you remember, masks are just like the actual areas of the objects themselves, not the binding boxes. And yeah, so as you can see, like Yolo V4 is a pretty significant jump, like in both speed and performance from V5. V3. And that's just a collection, and V3 is just the collection of orange dots at the bottom of the bottom left of the graph. All right. So now let's talk a little bit more about the structure for V4. The system starts with the input layer for the image. Then it's processed through the backbone for feature extraction. This information is then sent to the neck to enrich the spatial information in the network that's sent to the head. So yeah, so that information is sent to the head for dense prediction or object detection. And if you look at the diagram, you'll notice that there are multiple layers of the neck that are being sent to multiple layers in the head. And this is because the network is processing different spatial resolutions in order to detect objects at different scales or sizes. And yeah. So now let's take a look at Backbone in a bit more detail. And so to improve accuracy, one of the things V4 implemented was just like having a deeper network. And this increased like the detail of the extraction process, but it also increased like the model complexity. And one way V4 did this was by increasing the size of its dense net. And a dense net is just composed of a bunch of dense blocks with convolutions and poolings in between the blocks, which ultimately lead to a prediction, as shown in the horse picture here. And an individual dense block, as shown on the left, is composed of a series of even more convolution layers with Rayleigh as being the activation. And on the right, we have like an entire like, table showing the full architecture of DenseNet for V4. All right. And this isn't this is the only change made to the backbone. I'm only gonna cover two, but there were way more. And this particular change for the backbone is like CSP as I mentioned before. And what they did is that in the Darknet 53 architecture, which is like for V3 Darknet 53 was like the actual architecture diagram that's being used. What V4 did is that it implemented CSP in Darknet 53. And what this does is that CSPNet separates the feature maps input from the dense block into two parts, and this reduces the computational complexity. And CSP Darknet 53 also has a higher accuracy in object detection compared to architectures based on ResNet. The accuracy is also improved with the MISH activation as previously shown. So it's easy to see how all these things coming together like BOF and all these BOS methods, like all these things that come together like incremental improvements, they together like have a significant jump in improvement. Alright, so now let's talk more about the neck. And again, like the neck just provides a greater degree of spatial information to the head and for the final predictions. And one way V4 accomplishes this is with a spatial pyramid pooling layer, or SPP. SPP applies a different strategy in detecting objects at different sizes. It replaces the last pooling layer, which goes after the last convolution layer, with a spatial pyramid pooling layer. And SPP is primarily used to retain the spatial dimension of the output by concatenating the feature map from different kernel sizes, as shown by the diagram on the right. Okay. Now let's move on to Yolo V5. So Yolo V5 was released around the same time as Yolo V4, and the controversy surrounding the naming was probably due to the ambiguity in who would continue Yolo. This is where Ultralytics, a relatively new AI research company, comes in. with their model Yolo v5. So they have four versions of their model: 5X, 5M, 5L, and 5S, which differ slightly in their architecture, with 5X being the slowest and most accurate model. And as a side note, I actually met the creator of Yolo v5. I'm Glenn Josher. He's a super nice guy, and I worked on their model for mobile applications, for my own like app and my own safe computer vision research. All right. So now let's take a look at the comparisons of V5 and just other models, and you'll notice that this model is actually not a significant jump from even V3, and it's actually like worse than the recent versions of Yolo V4, and as you can just see in the graph, and this wasn't really the goal of V5. The V5 the goal of a company and just like the model, it wasn't necessarily to like just have like a massive jump in accuracy and accuracy and speed. Although that would be a great perk. The company Ultralytics, their goal was to just make training easier and more accessible to customers. And they are a company after all. So fundamentally, what's really important is their relationship with the customers. And one way they accomplished this was with something called an autoencoder, which I'll talk about more later. Finally, there's also like a bit of controversy with comparisons made between V4 and V5. And this is because Alexei, he claimed that the hyperparameters used for training V5 were not the same as V4. For example, he said that the input sizes for images into V5 was slightly larger, which means that V5 would be like more accurate regardless of like what you do. And so the graph you see here was actually provided by Alexei, who I guess like was like mad enough to just like train it on his own. And I think this is probably like the most consistent graph you can get between them. Probably has like yeah similar batch sizes, similar epochs, similar like image sizes. Yeah. All right. So let's actually talk about some of the like major advantages of Yolo v5. And one of their like major like innovations was mosaic augmentation. And this is just a data augmentation method where you tile four images together into one big image, as shown by the image at the top. And Yolo 5 then applies like another set of data augmentation techniques on top of mosaic augmentation. So like for example, they can add noise or they can like change color of the image. And this is particularly helpful in the Ecoca dataset to help the model not overemphasize large objects during training. However, if your like dataset has a bunch of smaller objects, mosaic augmentation actually hurts it. And this method was actually referenced in the Yolo v4 paper and was credited to Glenn Josher, which is a pretty big deal. Also, like as a side note, Yolo v5 is not actually published research. This is like, another like reason people don't necessarily see it as legitimate. Whereas like v4 is like pretty well documented and pretty like well, I mean it's published and it's pretty well recognized because of that. And yeah, anyway, so like another innovation in v5 is their autoencoder. So the autoencoder, the goal of that was to just like have a better set of anchor boxes if the algorithm finds that your current anchor boxes don't match your dataset very well. In terms of aspect ratio patterns, like as we saw earlier. And like if you recall, like the way V2 and V3 do it is that they refine their anchor boxes like through IOU and k-means clustering. Well, Yolo v5 took a different approach and used the genetic algorithms to refine anchor boxes. Genetic algorithms like essentially mimic biological evolution in that they're parents whose traits you pass on with the possibility of mutation. In this case, the traits are the attributes of the box. And after running through the genetic algorithm, you get a couple thousand really good anchor boxes that you use for training. And one of the major benefits of not just V5 but Ultralytics as a company is their mobile implementation of Yolo. So through CoreML and their O1NX model, they're able to utilize the neural engine on the iPhone to process images at 5 to 10 FPS. And just take a moment to appreciate that. Like these processes are usually run on GPUs, but through Apple Silicons, you can run it on an iPhone. And I just think that's really cool. And the really fascinating part is that their accuracy when actually like detecting stuff on an iPhone, it's really like not too different from what you get on a GPU. So that's just really really impressive. So yeah, anyway, how does this like process of compressing the model down to an iPhone work? Well, what Ultralytics did is that they first rebuilt the darknet architecture with PyTorch, and then converted that to the O1NX format, which stands for Open Neural Network Exchange. And as the name suggests, it's sort of this universal format for computer vision models, which allows you to plug this in into all sorts of applications, including on mobile. Then you have to use like a bunch of tools to convert the model to Cormel, which is Apple's like format for models. And then you can just like run it on whatever app you want through Xcode. Yeah, and as always, if you're interested in looking at the primary sources for each of the Yolo versions, here they are. I also included my paper from last year, and that didn't really include some of the stuff I talked about with V4 and V5 because it wasn't really like V4 and V5 weren't that well known last year. But like right around the time I released that paper, V4 and V5 were released, so that's kind of funny. I also included the paper for mask RCN if you're interested in instance segmentation. And yeah, so like that's all I have, and I really hope you enjoyed my lecture.